problems related to stability of Carbanion. And to understand the explanations easily, please watch the previous videos, especially part 3 and 4, where the factors responsible for stability of Carbanion I have discussed. Okay, and playlist link for all the videos of Carbanion chemistry you will get in the description box. The first problem, here we have total 4 carbanions, Me3C minus, Cl3C minus, then Me2CH minus and C6H5CH2 minus, in order of their decreasing stability. Now here in the first case there are total 3 R group, so it is basically Me3C minus, then we have 3 chlorine which is having minus I effect. In this case we will have plus I effect, and then we have Me2CH minus. Now again there are 2 R groups which will be providing plus I effect, and also in the last case we have PaCH2 minus. Now in this case there will be mesomeric effect, so the negative charge that will be taking part in resonance with the double bonds present in phenyl ring. So there are different factors responsible for this. So in the first case, negative charge highly dispersed because of minus I effect. Then in this case, that is PHCH2 minus benzyl carbanion, here negative mesomeric effect that will delocalize the negative charge. Then we have plus I effect. Now when it is plus I effect, obviously these two we will place at last. So among these two, Me3C minus, that will be least stable. This will be minimum stable because there will be total 3 plus I effect, but here we will have only 2 plus I effect. So that is why this will be at the minimum point. Now Me3C minus, that we have at the last point only for option B and option C. Okay. Now these two obviously not correct. So in this way we can choose B and C. Now after that, obviously these two will be at last point. So that is why if you compare between B and C, after Me3C minus, the next stable is Me2CH minus. But in option B it is PHCH2 minus, but that cannot be true because in this case we have minus I effect. So after that is the minimum stable Me3C minus, the next one should be Me2CH minus. So this much information is enough to choose that correct option should be option C. Now why between these two CCl3 minus is more stable? Now it is true that we give more significance to which effect? Resonance effect. But here as total 3 minus I effect present coming from 3 chlorine, so that is why this factor now it will overcome. It will overrun the resonance effect. Another point of view also, you can compare these two, though we have already chosen our option, but exact explanation if we want to understand. The corresponding acid is CHCl3. Just add 1 proton, and in this case it is basically toluene, PHCH3. Now in these two, which one is more acidic? Obviously CHCl3 is more acidic. Here pKa value if you see, basically it is hydrocarbon, and here we have, with this hydrogen we have 3 Cl groups, so obviously it will be more acidic. And we know when we add 1 proton to the carbanion and you are getting the acid, it is more acidic. That means the corresponding conjugate base of CHCl3, which is basically the carbanion that is given in the question, that will be more stable. So that is why this is another way you can give the explanation for it. But whatever it is, correct option is this one. Next question, which of the following carbanion has the highest stability? So here we have 1 point common. So this part is basically common for all these 4 species, and another point is common, all the groups that are present at para position. So we just have to check among these 4 groups in which case there will be donating effect, in which case there will be withdrawing effect. So CH3 and OCH3, these two, CH3 basically it is always plus I, and OCH3 as it is present in at 4 position, so it will be providing plus R effect. And these two are basically electron withdrawing group. Now among these two electron withdrawing group, which one is more electron withdrawing? It is obviously the NO2 group. So that is why among these 4, NO2 will be giving maximum withdrawing effect. So that is why it will be more stable. So CH3, that is this methyl group, it shows plus I effect. Then OMe shows plus M. This is plus I, this is plus M. So obviously these two are not our answer. And What about the next two? Both NO2 CN minus, there is minus a M effect, mesometric effect, but NO2 is having more mesometric effect, so that is why this will win. So correct option is this one. But suppose the question is framed in a different way, that you have to arrange them according to stability. Then first point will have this one, that is number 4. Then we will have number 3, that is a CN, then OCH3, and then CH3. Sorry. OCH3. It will come at last, not this one, because it will have more plus M effect. Okay, but here our answer is the last one, because it is not asking sequence, it is just asking which is having the highest stability. So here if I show what kind of resonance will be there, it is basically, so now the double bonds, they are shifted. Here we will have CC double bond and negative charge will be over nitrogen. So in this way the minus M effect, that will be operating. CH2, then here we will have plus, O negative, O negative. Okay, so correct option is last one, which is having high stability. So in the first species there is negative charge present directly over this carbon, which is that is part of triple bond. So obviously it will be having stability. Now what about the other species? Here this negative charge, it can undergo resonance with this CC double bond. The same type of resonance it is also possible in the pH ring. But in the last one, if you see, here we will have plus I effect, that is coming from 3 positions. 3 methyl groups are there, so it will not be stable at all. It will be highly unstable. So based on this we can choose that the first one, as it is directly negative charge is present on the carbon, which is having that is sp hybridization. So based on that, this will be maximum stable. But if we want to see the order, that is, this is the maximum stable, the last one, that is minimum stable. Now what about the middle two? If we want to see that, then we can take the help of pKa. So in the first case, if you just attach one proton to each species, I'm not here, we don't have the acid which is coming from 4 because it is minimum stable, so we are not discussing anything related to it, only focus on 1, 2, 3. So from the first carbanion, if you add one hydrogen, you will get this species, that is basically acetylene. Then we will have the second species, and the third one, that is toluene. So if you look at the pKa value, obviously the first species, that is the most stable, but that is fine. But what about the other two? So in this case, basically this carbon is sp2, here also this is sp2. In both cases resonance is possible, right? Now you can say that here we will have two resonance, one resonance structure, and that is considering this the first species, and after resonance there will be two structure and both are equivalent. But in the second case, when there is resonance, then the aromaticity factor is lost. So from that point of view, that is basically another factor which is not very stable. That is, when there is resonance occurring, it is okay, but still there is aromaticity is lost. So that is one point. But still, if you look at the pKa, this species is more acidic. That means the carbanion that you will get from it, that is species number 3, that should come at second point after 1 according to the pKa. But what explanation we can give that why the second one is more stable? Another explanation also you can give, that if you consider this carbon and that it is attached to 2 hydrogen and 1 carbon, here also it is attached to 2 hydrogen and 1 carbon, then come to the next point. Here with this carbon there is basically 1 hydrogen, this one. But here if you go to the next carbon, we have 2 carbon both sides. So that is, though it is not very good explanation I will say, but still if we want to give explanation for this very little difference in pK value for these two species, we can say that here both side we have carbon with this, but here we have one side carbon, another side hydrogen. And carbon is having slightly more electronegativity than hydrogen. So that is another point we can say. It is overall from this part, it is having more electron withdrawing effect. So that is why this carbon is more stable. So though we have already obtained our answer, which is 1, but if we want to see the order, then after 1 it should be 3, and then 2, then 4. the stability order for the following carbanion is. So here we the answer by mistake I have selected, that is P, R, Q and S. But why it is so, that we have to see. So P, that is the first species, then Q, then NO2 at 4 position, and then we have there is no substituent in the last species, right? Now one factor is common, that is this part. So all of this carbanion, it is basically, that is this part is common, and in the last species there is basically no substituent. Now in this case NO2, it is at 2 position, in this case it is at 3 position, and in the third case it is at 4 position, and in the last case there is actually no electron withdrawing group. Now NO2 group, it has minus I effect as well as minus M effect. Now minus I effect is applicable from any position, but when we are talking about minus M, it is basically possible when it is at position 2 or it is at position 4. Now obviously when it is at position 2, the minus I effect is high because it depends on distance, and minus M effect, it is already there. So that is why P should be maximum stable, and after P, in third species, minus M effect and minus I both are applicable. So that is why after P there will be R, and then at the third position NO2 group, it will be providing minus I effect only, but still with respect to the fourth species it is having more electron withdrawing effect, because here if you compare the same position there is hydrogen only. So that is why after R it is Q, and at last we have S. So P, that is the first species, ortho, then para, then meta, and at last one the simple benzyl carbanion. Okay, so this is the answer. Match the following carbanions with their corresponding half-lives. Half-life, if we want to correlate with stability, basically it is not directly asking the stability of carbanion, but it is asking in a different way. That is, we have to match the half-lives, but basically it is related to stability, because when stability is very high, stability high means what? Its half-life, that will also be high. Okay, so it is directly related. So here we will look at the carbanions. This part, if you see, for the first 3 species, it is CH minus CH3. So this is common. So there is plus I effect coming from CH3, but that is in the 4th species it is completely different. It is not at benzyl position at all. So here resonance is not possible. When I am writing R, it means resonance. Here resonance is not possible. So that is why it will be having the least stability, minimum stability, because there is no plus or effect minus basically, that is resonance with benzene rings double bond, that is not possible in this case. So this should be the minimum stability. That means its half-life, that should also be minimum. Now minimum half-life, if you look at the order for 10, all are negative. So this is basically minimum. That means D should be related to P. Now D is related to P, that you can get in option 1 and 2. Now come to ABC. In ABC, the common part we have already chosen. Next we have this alkyl group at 4 position, and then we have NO2 group at 4 position. So here it can show minus M effect as well as minus I effect. So that is why it should be having maximum stability. Now B is related to maximum stability. That means if you look at the power 10 to the power minus 4, this is minimum. That means this overall value, it is basically high. So B should be related to S. Now we have already chosen 1 and 2. These two we have cancelled. Now B is related to S, that we are getting in option 1. So that is why this should be the correct option, that is option 1. But why A is related to R, B is related to S? Now the second half-life value, that is basically Q, 10 to the power minus 5. After minus 4, 10 to the power minus 5, that is the next minimum value. So that is why it should be related to C, which is this one. Because with respect to this alkyl group, here OCH3, it is true minus M effect not possible, it is at meta position, but minus I effect, that is basically possible. Oxygen is electron withdrawing. So that is why it is more stable than A. So basically stability order is first B, then C, that is NO2, then meta OCH3, then it should be A, and the species D, it is completely different types of species. Here negative charge, it is not at benzylic position, so resonance with benzene ring not possible. So this is basically the minimum stable. So option 1 is the correct option. Okay. The stability of Carbanion in the following, here there are total 4 species, and this is basically related to hybridization factor. So if you see, in the first case, the hybridization is basically sp, then for species 2 and 3, the hybridization is basically same, sp2, sp2. So these 2 carbon I am marking here, this is sp, sp2, sp2, and then we have sp3. Now from the hybridization only we can understand that 1 should be maximum stable, then 2, then 3, then 4. So correct option is option C, right? But if we want to give the explanation that both are sp2 but still 2 is more stable, now the same type of explanation that I have already given, that you can apply here. So with this carbon which is carrying negative charge, both side we have carbon, but if you focus on this carbon, this side we have carbon and another side we have hydrogen. Now carbon is slightly more electronegative, so that is why that may be an explanation why it is more stable, because both are sp2. So option C is the correct option. So that's all I have for you in this video. Thank you for your time.